Okay, hi, welcome back. This is now chapter 2 in differential equations, and we're looking at solution curves. Given that you're not necessarily, that you might not even have a solution, you could still kind of see what the solutions will look like just using the differential equation, presuming that it's one of these special types. And so let's take a look at it. So first, note that we can use these differential equations if it's in the, I guess they call it the normal form. We can use that to determine the slopes of the solutions at any given point. So on some interval of definition I, the solution y equals y of x of the differential equation in the form dy over dx equaling f of xy, that thing will have no breaks and has tangent lines at each point. Okay, the solution of that thing will have, so it's continuous, so it'll have no breaks and it'll have tangent lines. What I mean by tangent is that the solution curve at any given point, you can get its derivative. So you can evaluate the tangent line to the curve at that particular point. And what we're going to be able to what we'll do is create what's called a direction field based off of all those little tangents. Okay, so it will have tangent lines at each point, x comma y of x. Okay, so direction fields. That's what we're going to build with these little slopes, and the book calls them like lineal elements or something like that. It's basically like a vector field, except all the vectors have the same size if you've taken like Calc 3 or something. But anyways, a direction field or a slope field. Let's build one so I can actually show you what this is like. I just took number 1 from the homework. So they give you this dy over dx equals x squared minus y squared. So what we're going to do is evaluate that derivative at a bunch of points and then draw little itty bitty tangent lines at each point, and it creates kind of a maze type thing, and you're able to draw your solutions through it. Okay, so we'll call f of xy this x squared y squared thing, x squared minus y squared, and then we're going to evaluate that thing at like 9 points around the origin. So, oops, start at -1, -1, and then just go on from there. And we're just plugging those numbers into the f of xy there. So -1 squared is 1, minus -1 squared is 1, so that'll be 0. -1 squared is 1, minus 0 is 1. -1 squared is 1, minus 1 squared is -1, so it's 0. 0 squared is 0, minus -1 squared is 1, so it'll be -1. Then 0 minus 0 is just 0. 0 minus 1, 1 minus 1, 1 minus 0, and then 1 minus 1 is 0. Okay, so I'm going to come over here now to my xy plane and put little tick marks at each one of these points that represent the tangent line to the solution curve that would go through that particular point. Okay, so -1, -1, let's put it in red or something. So we have slope of 0, so that's just a horizontal line. Negative 1, 0, slope of 1, so you go up 1 over 1. So you'd have a little line going up. Negative 1, 1 is back to 0, so horizontal slope. 0, negative 1 is down here, so that's going down 1 over 1. Should look like that. 0, 0 is just 0 slope, so horizontal. 0, 1 is going down 1 over 1, so that. 1, negative 1 is 0 again. And then 1, 0 is positive 1, so going up like that. And then 1, 1 is 0 slope again. Okay, so in general, you have a computer do that for you. You don't have to do it by hand. And what's going to happen is you'll get a big picture like this on the right, a bunch of little tick marks. And you can kind of see where my tick marks are. They are right in this kind of square region here. And you'll see my tick marks are the same as the little arrows that they have drawn there. Okay. Usually in most computer programs, you have to use a vector field to graph this. They're not going to have like a slope field generator. Like I said, you have to use a vector field and then normalize all the vectors to the same size. But anyways, once you get that field generated, then for any point in this field, you can kind of crawl out a solution by just following the little arrows, right? So, and the first couple problems, that's what they'll have you do. And first off, you have to make sure you have the right field. So anyways, at y of negative 2, they want you to sketch out an approximate solution at negative 2, 1, right? So negative 2, 1, 2, 1. The solution would go through the second quadrant. So the first two aren't even right. It's this third one that has to be the correct solution because it goes through negative 2, 1. And then to draw it out, you're just basically following the arrows. So us humans will probably have, multiple different looking answers for every person that draws it. But okay, and then like 3, 0, the one that goes through 3, 0. So that's just a 1, 2, 3, and then 0. So it should hit right here. So I guess it's this one. This one doesn't go through that point. This one doesn't go through that point. This one doesn't go through the point. 0, 2, it has to go through 0, 2, right? So it has to go through the y-axis up here at 2. The only one that does is this one. 0, 0, it has to go through the origin. So this is the only one that does that. And then just they have a bunch of the same problems here. Okay, so the point is, even though you don't know what the solution is, you don't have right now the methods for solving this differential equation, we can get kind of a graphical approximation to it just using the this differential equation, just plotting a bunch of points and doing a bunch of line elements. Those problems are pretty much all the same. Only one that's even a little bit different would be like number 7. Number 7, what they do is they give you the graph of the derivative there, the dy over dx, and then you have to generate the slope field from that. So let me take a quick look at that and see how it goes. Okay, so this is number 7 in WebAssign. Go back to black. So draw this thing out. So this is the graph of the dy over dx. They're not going to give it to you, but they are telling you it's only dependent on y. So there's no x part of it. And what does that mean? That means all of the tick marks are going to be kind of going in the same direction at any given line y equals c, or y equals, like y equals 0, all the little tick marks on the x-axis are going to be going in the same direction. Okay, all of the lineal elements or line elements, whatever they're calling them. Okay, so let me try to sketch the function here. Going up to 2, maybe down to 2, and it looks like it's starting up and then hits the x-axis and then goes back up. whoops, it goes through 1. Let's try that again. So it's going down like this. I should have 3 tick marks there. I think that maybe that's my issue. Ugh. Sorry. Okay, so it's, starting up and then going down and then going through 1, hitting 2, and then just kind of zipping down like that. Okay, so basically you use this to okay, so let me draw the XY plane. And this would be like your y, and this function here would be f of y. Okay. So when y is equal to negative 1, 2, 3, so y is equal to 1, 2, 3, all the little tick marks are going to be positive, like positive 2, so going up like this, and then they're going down a little bit, and then eventually 0. Okay. So at again, at negative 3, all of the tick marks are positive, going up like this. And it's not dependent on x or t for time, so it's all the same for any x value. And then as I get closer to 2, it's going to level off to 0. So somewhere in between negative 3 and negative 2, it actually goes horizontal, like this, and then it'll become negative at negative 2, so you'll have some negative type slope going down through like this. Okay, and then finally it's going to zip back up, so it'll become less and less negative until it hits 0 again, so you have 0 slope at y equals negative 1, so it'll go like this, and then it'll increase in the slope, the lineal elements will increase to 2 in the region between negative 1 and 0. So it'll increase. And then just keep increasing all the way until it goes to right before 1, and it'll go 0 again in here somewhere. Seems like it's leveling off a little before it goes 0, so we'll kind of try to make it level off a little bit. It doesn't have to be perfect. And then it'll just start going negative big time. Okay, so kind of negative at first, and then over time it'll get worse and worse. So more vertical. Slope. So this gives a kind of a description of the slope, yeah, it's a slope field, basically. It's not even a description. So looking at the given A, B, C, D, you just have to match up your tick marks with theirs. And the first, this example here, they're all going up in that upper part, but they should be going down, right? So that's not going to work. This one's kind of oscillating, and we know it's dependent on y, so it wouldn't do that. This one looks correct. It has the horizontals is kind of a good place to check at about 1, and then negative 1, there's a horizontal, and then there's a horizontal at negative 2 point something, and that's different than this one over here. So it's going to be this choice. Okay. All right. So in this example, you kind of see there's these places where you have like horizontal asymptotes, and in there. It kind of subdivides everything into about what 1, 2, 3, 4 regions. Okay, and that's the kind of behavior we want to look at next. This thing is actually what they call an autonomous first order differential equation. Okay, so that's where we'll go next. Section 3, autonomous first order. Instead of writing out differential equation, we'll just put DE. Okay, so these guys are only dependent on y. Okay, and what we're going to do is create these things called phase portraits out of them. And again, it's kind of a quick hand way to analyze the behavior of the solutions without actually having to get the solutions. Okay, so again, let's just remind you of the difference between an autonomous and non-autonomous. So and we're not saying it just has to be some variable in terms of just one variable. In particular, it's the dependent variable that we need for autonomy. So this one is autonomous. This example here is not. So dy over dx equaling xy squared. It seems like even if it's in terms of just x, it should be considered autonomous, but I believe the book will just will restrict themselves to functions of y, I believe. Okay. An ordinary differential equation in which the independent variable does not appear. Okay, so the independent being x. So this guy is non-autonomous because the x is there. Okay, so hopefully that's quite clear. We've made an additional assumption here in the book. So you're usually assuming that we're on some interval of definition, and for this part, we're assuming that f and f prime are continuous, which is the criteria for having a unique solution, okay, from previous sections. So let me just note that here in this section, we are assuming f and f prime are continuous on some interval. Okay, the first thing we will note are what they call the critical points, and that's where we're taking the derivative and setting it equal to 0. Okay, so the critical points, these are the points C where f of C is equal to 0, and note if C is a critical point, then you have a constant solution going through it. Okay, so then y of x equaling C is a constant solution. Okay, so first let's just look at finding these constant solutions, and then from there we'll try to do like a phase portrait, and we'll see it's kind of easy to get the slope field, and then we'll move into the phase portrait. Okay, so here we are. I'm taking these problems from WebAssign. So we get y squared minus 4y. So note the critical points. We take the derivative here and set it equal to 0. Solve for y. Okay, so y times y minus 4 is 0. So our critical points are y equals 0 and y equals 4, and those are both constant solutions. From here, we can quickly draw the slope field, right? So at y equals 0, your lineal elements all be horizontal, and then also at y equals 4, your lineal elements will all be horizontal. And then in the sort of the in-between regions, so there's going to be 3 regions, right? R1, R2, and R3. Because of this continuity that we've assumed, we can say that the solutions in those regions will all kind of have the same behavior. They'll be going up or down. So let's figure out what the derivative is in those regions. So in region 1, this is 4 and this is 0. In region 1, you have numbers like y equals 5. So basically, you could just do a test value and plug it into this equation here, and that would give you the sign of the derivative. So when y is 5, you'll have a positive 5 times 1, positive times positive. is positive. So your lineal elements in that region will all be going up, basically. So they'll all look like this. And your solutions in that region will have that behavior as well. Okay? In this middle region, R2, from 0 to 4, if you plug in like y equals 3, you get a positive times a negative, so y prime will be less than 0. In other words, solutions in that region are all going to be decreasing. Okay, so they'll be going down like this. And then that third region, R3, if you do a test value like -5, you have a negative times a negative. When you're, again, I'm using this equation up at the top here in the box. So in that case, you'll have y prime greater than 0, and all your lineal elements will kind of be going up like this. And from that information, you could do guesses on kind of how the solutions look. They'll probably be going up like that and there, down like this, and then like this in this region. Okay. From there, we're going to produce what's called a phase portrait, which is just a vertical line, and on the vertical line we'll put dots for each critical point, and then on the line we'll put arrows indicating the direction of travel of the solution. So in this region it's greater than 0, so you go point up. In this region it's decreasing, so point down. This region it's going up, so point arrow going up. Okay. Okay, then so this vertical line over here is the phase portrait. So let's talk about then the phase portrait and give some characteristics of it. So section 5, phase portraits. This is a graph of the critical points and the signs of the derivative. So graphs of the critical points and signs of derivatives. So just an example that kind of hits everything at once. There's 3 kinds of points. There's stable, unstable, and semi-stable. So I kind of just want to go through those. And then on top of that, we'll talk about kind of the behavior of the solutions in these regions. Okay. So let's put 3 points on here. And, each one of these represents a critical point. It's subdividing the region into 4 areas. Call this one R1, R2, R3, and R4. Let's say the first region, the derivative is negative. In that case, the arrow will be going down. Let's say the second region, the derivative is positive. So in that case, the arrow is going up. When you have 2 arrows pointing at a critical point like that, they're going to call that stable. There's a couple other names for it, but I'm just going with the name that they give it in the homework. Okay, so that one will be stable. When the arrows are going away from the point, so if region 3, you found that derivative was less than 0, the arrow is going down, that's called unstable. Okay. And the other words are like repeller and attractor, and actually those words seem more familiar to me dealing with other like nonlinear equations, but we'll just go with what the software wants. The fourth region, the derivative y prime is, let's assume it's negative. So if you have 2 arrows kind of going in the same direction around a critical point, they're going to call that semi-stable. Okay, so some characteristics about solutions in these regions, and again, we made some preliminary assumptions back here in the beginning, assuming that f and f prime are continuous. So the first presumption is that solutions can't intersect, and that's just a point about uniqueness, right? So solutions can't intersect. Secondly, solutions in subintervals will always increase or decrease. There's because of the continuity of the derivative, it's not going to be able to go and change sign on you in a subregion. Okay, so solutions and subintervals are always going to be increasing or decreasing. Solutions and subintervals always increase or decrease. And with that in mind, solutions over time, if it's increasing and bounded above, it will sort of level out to the critical number that's above it. If it's a decreasing region, the solution will level out to the critical number below it. So you could make presumptions about the behavior of the solution over time. Okay. Thirdly, if you begin in a subregion, you will stay in that subregion. Okay. So solutions in a subregion will stay in a subregion. Okay, so anyways, let's kind of investigate one of these problems. Look at number 12. Dy all over dx equals y ln of y plus 2. So there's some restrictions on the y values here because of the natural log. I would just note that y has to be greater than -2. So when I go to my phase portrait, I'm not going to go below that value. Okay. So let's pretend this is -2 here. I need my critical values. So over here to the top right, let me set y ln of y plus 2 equal to 0 and solve. So one solution, y equals 0. The other solution, we have a natural log equation to solve. Ln of y plus 2 is 0, so you can go e to the 0 equals y plus 2. In other words, y plus 2 equals 1. In other words, y equals -1. So those are our critical numbers. Okay. Let's go ahead and put those on our phase portrait here. So -1 and 0. And then we'll put kind of a slope field right next to it. And anyways, on the phase portrait, let's get the derivatives going. So the sign of the derivatives from 0 to infinity. If you put a number like 5 into, let's put it, I'll circle it in red. We're going to play with this function here. So if you plug like a test value y equals 5 in there, you'll get a positive times a positive. So in that region, the thing should be increasing like this. Okay. If you put like -1/2 in there, you'll get a negative times like ln of 1.5 will be positive. If the input of ln is less than 1, it will be negative, but it's still above. So it'd be a negative times a positive. In other words, it's decreasing in this little interval here. And then finally, try something like -1.5, and finally you get a negative times a negative value, so it'd be increasing. Classify the critical points. So this guy is a repeller or unstable. And then this other guy is an attractor. In other words, it's stable. And then, of course, down here, the solutions will be going up like this. And you can kind of draw out potential solutions. So stuff would be going like that in that region, like this in this region, and like this in this region. And then, yeah, let's look at the problem in that section. Which number is this? 12. Yeah, so first they want the phase portrait. And you can see I got the phase portrait here. And then they want you to list the types of critical points. So -1, again, is they call it asymptotically stable. And then 0 is unstable. And then there aren't any semi-stable, so you just type in NONE in capital letters. And then Yeah, so in the first region, it's increasing, so you can't include this one. The second given solution has looks like it has critical points at 1 and 0. And our critical points are at 0 and -1, so you throw that out. 0 and -1, 0 and -1 for both of these, but the first region is increasing, not decreasing, so it has to be this guy as your solution. Okay, let's look at number 14, and then we'll kind of call it quits. It turns out that we're not going to do much with this type of work. This type of work is really good for analyzing nonlinear systems when you don't necessarily have techniques for finding solutions. And we don't really look at nonlinear stuff, so we're not going to focus too much in on this technique, so don't get too carried away with it. If you're interested in like nonlinear stuff, you could read that book by, what is it, Stogratz or something. He does a lot of this. Stogratz, is that his name? Yeah, Stephen. He's at MIT and he does all kinds of stuff with nonlinear differential equations, and a lot of his techniques in that book are like the techniques we're giving you right here. He also did a big study on fireflies, and he noted that, well, I think for a long time people knew that fireflies would kind of sync together, so they would start out just sort of randomly blinking, and then they would all be in unison. I don't think that works here in Ohio. I don't think our fireflies are that smart, but in other countries they do that. But he analyzed them and then looked at pacemakers and stuff like that. Okay, so anyways, let's look at number 14. Let's see what we got here. They gave us an autonomous differential equation for an object that's falling, and then it has this wind resistance term as well. Let's go ahead and clean it up first. dv over dt equals g minus kv over m. Instead of y, the dependent variable is v. Okay, so this is autonomous. Let's get the critical point. So all you have to do is basically set the g minus kv over m equal to 0 and solve for v. Okay, so adding kv over m to both sides, you get kv over m equals g, and then solve for v. So v equals gm over k. That will be our critical value in our phase portrait. Okay, so we have this guy, gm over k, and that'll be kind of our kind of horizontal asymptote kind of thing. Above that, when you go above gm over k, this will be going negative, so we'll be going down like this. And then below it, you're going up. Okay, so it'll be positive. So as t goes to infinity, it looks like we're always going to be going towards this critical number. So yeah, the limit as t goes to infinity, the velocity will be that critical number gm over k. And what kind of point is that is kind of the second question. And of course, that's a stable point. Okay. I don't know why, but it should be stable. Where's the stable? There it is. Okay, so that would be the answer. Okay, I think that'll do it. Like I said, don't get too carried away with this. These methods we're not going to be using throughout the book. But if you are playing around on your own and you get a differential equation you can't solve, you can use these methods to get an idea of what the solution looks like. Okay, so let's leave it at that. Oh, I didn't give you a video quiz question. We'll say number 12 is the video quiz question du jour. Okay, so number 12 is the video quiz video quiz, video quiz, video quiz, video quiz, video. So you can pause the video and just copy that down, and that would be good enough. Okay, so we'll see you next time. As usual, thank you for watching.